Hello, hello. Okay. So people have been saying on Piazza that they can't hear me. So I maxed out the volume. That's probably too much for those of you in the class. But hopefully it will be audible now. All right, so what are we going to do today? So last week we talked about in the first lecture we talked about some of the most popular signals like the impulse, the unit step. Well, of course there's more. And the most important class perhaps for the purposes of this course is the exponential signals. Okay, so if you're in continuous time, that means you have a signal of this form, e to the st, all right? For now, think of s as being a real. So if s is positive, that means you have a function that is growing, well, exponentially, right? And if s is negative, that means you have exponential decay, right? Asymptotically converge to 0. Okay, and then in discrete time, x of n, what would be the equivalent of an exponential signal? You don't need e anymore. Yeah, but forget about the system. Just tell me the signal. You had one. Sigma over power n, right? Something to the power n. Is that what you're saying? Okay. So I'm going to call that number z for now. Okay. Actually, I'll call it z always. But for now, let's assume z is positive and real. Okay, so, and then there are again two cases. If z is bigger than 1, then this is going to keep increasing exponentially, right? And if this is, if z is smaller than 1, then it will decay. So it starts at 1, and then next time it's equal to z, next time it's equal to z squared, etc., right? As a function of n. And then z between 0 and 1 would give us something that starts at 1, but then is getting smaller and smaller. And as z gets closer to 0, it goes to 0 more and more quickly, right? So you all see that, right? So for real s and real z. Okay. So the purpose today is to disappoint you by getting rid of r, generalizing to complex numbers, okay? There they come again. I know. Okay, but you'll appreciate complex numbers at the end of this course. They work wonders for us. They are amazing. They simplify everything. Okay, any questions? Yes, among other things, we can now represent oscillatory signals as exponential functions. So that's one of the benefits, but there are many more, okay? So I won't even list them. So let's start with a very quick reminder of some tricks with complex numbers. And some of these things will be obvious, so just bear with me. If nothing else, this will help us set the notation. Okay? All right, complex numbers, there you go. So a few things to remember about complex numbers. So we usually write a complex number as the real part, which I'm going to denote with sigma, okay, plus I or j, depending on your taste. I'll go with j, where j, of course, means square root of negative 1, okay, times omega. So sigma is the real part, and omega is the imaginary part. All right, so that's very basic so far. Then the conjugate of this complex number will be denoted as star in this course, all right? So that means keep the real part the same, switch the sign of the imaginary part. And obviously, if you multiply z with z star, what do you get? You get sigma squared plus omega squared, which you can call the magnitude of z squared, right? So that brings us naturally to, before that, let's also note that if I add to z its conjugate, the imaginary parts clear out, so I'm left with 2 times the real part. And if I subtract from z its conjugate, then the real parts cancel out, and I'm left with 2j times the imaginary part. All right? Now, so this sort of is a Cartesian representation of a complex number. We also deal with the polar representation, where we imagine a plane where the horizontal axis is the real part. No, not the real part was sigma, right? Sigma, and the vertical axis is the frequency. So then, based on what your sigma is and what your omega is, you're going to have a number represented as such, right? The polar coordinates means that instead of keeping track of the real and imaginary parts, you keep track of the magnitude. So call that r. So r is the magnitude of z. So z is this number here, of course, it's complex. And then we need this angle. And that angle, of course, you can get from the inverse tangent of the vertical value omega divided by the horizontal sigma. Okay? And sometimes that's called, the angle of z. So this notation here means the angle. Okay? It's just like, what were those gadgets called in the old days? I had one in elementary school to measure angles. Oh yeah, okay. So I think that symbol is supposed to be sort of a replica of that. Okay. So the important thing in this course is this identity, which interprets e to the power an imaginary number as being cosine of theta plus j times sine of theta. All right? So that's essential for this course, really important. You have to know this, okay? You can't do anything without knowing this, all right? And then if we take this into account, then we can represent z very concisely here. So as you can see, e to the j theta has real part cosine theta and imaginary part sine theta. That means it has amplitude 1, real part cosine, and the angle here is theta, right? So to recover our complex number z here, all we have to do is to scale this picture here, which has amplitude 1, magnitude 1, multiply it by r. So I can write z as r e to the j theta. All right? So this is the polar coordinate representation of a complex number. So in polar coordinates, the conjugate can be stated as, remember in the Cartesian coordinates, we just flip the sign of the imaginary part. In polar coordinates, r doesn't change, of course. What happens to theta? It changes sign because now we have negative theta, right, going in the opposite direction. So this is going to be our z star, right? So r is the same, but now we have negative theta. All right, so, and with this, of course, some of the things you, like here, when I said z times z star is equal to, sigma square plus omega square, those types of things are pretty easy in this representation. because z times z star is simply r e to the j theta and r e to the negative j theta, so you simply get r squared, right? Makes sense. So in fact, that's one of the benefits of the polar coordinate representation. Okay, multiplication in general is easy, and we'll have to do a lot of multiplications in this course in dealing with systems, interconnections, and so on. Multiplication is easy in polar coordinates. If you represent one number, one complex number as r1 e to the j theta 1, and the other as r2 e to the j theta 2, their product is simply r1 r2 e to the j theta 1 plus theta 2. Okay? Amplitudes multiply, angles add. This would be much more cumbersome if you were doing this in Cartesian coordinates. All right, so a couple of more things. And if these are all super obvious to you, which is great, it should be, don't get a false sense of security. It's not like you're going to ace this course, okay? This is just to remind you and get you in the mood for complex numbers. Okay, so using this very important identity, e to the j theta cosine theta plus j sine theta, we can actually do all these trigonometric things that you perhaps did in high school or somewhere, right? All these identities, a lot of them actually become very trivial to derive, okay, without having to memorize formulas, right? For example, using this, I can express cosine of theta as e to the j theta plus e to the negative j theta, right? If I change the sign of theta, then cosine is the same, negative, but then sine will have the opposite sign, right? So if I add these two numbers, I get 2 times cosine. So if I add them and divide by 2, I get cosine. How do I recover sine of theta? Now subtract, right, the 2. So cosines cancel out, and you get 2j times sine theta, and divide by 2j. All right? What is 1 over j, by the way? It's a minus j, right? So this is the same as negative j over 2 e to the j theta e to the negative j theta. All right. Okay. So some of these trigonometric identities, such as, you probably saw something like this somewhere, cosine square of theta. You can actually write it as a constant plus cosine 2 theta, right? But what are those constants? So it's easy. If I just take this expression above here, it's just e to the j theta, e to the negative j theta, divided by 2 squared, right? So you're going to get the square of the first one, e to the j 2 theta, right? 2 times the product of these two. I'm just squaring the sum, right? And that will give me 2. And then square of the second number, e to the j 2 theta, and then divided by 4. All right? And that means I have 1/2 accounting for this term, plus 1/2 e to the j theta plus e to the negative j theta. But what is this? This whole thing. No, 1 over 4, I'm sorry. So this here is 2 cosine theta. So you get 1/2 plus 1/2 cosine theta. And there you go. It's one of those things in those tables of trigonometric identities, right? So easy to derive. All right? So are you becoming convinced that there is some value to these complex exponentials? Okay, yes. Yeah. Thank you. I should give you some points for every time you fix something, you get, We should find a system to do that. So at the end of the semester, when you come and say, I was so close to A minus, but I got a B plus, then I will look how many times you corrected me and you get a free ride. Okay. So where did these complex numbers come from in the first place? If you think about polynomials, you know, an nth order polynomial is supposed to have n roots, right? But sometimes they don't if you just look at the real roots, right? So complex numbers were invented to sort of fix that problem. That way, for example, when you look at a polynomial like x to the n, polynomial equality like this, right? Or x to the n minus 1 equal to 0, right? This should have n roots. 1 is obviously one of them, right? But what are the others? So this is called roots of unity. We should have n solutions to this. Only one of them, or perhaps two of them, being real. So how do we find them? Well, I can just interpret 1 as being e to the j 2 pi times some index, let's say k. If k is 0, then you have e to the 0 is 1, right? If k is 1, you have e to the j 2 pi, but that's the same as 1, right? Likewise, all integers will give you 1. But the advantage of that is now I can write the roots as this power divided by n. So I can say x equals e to the j, let's index it with k, 2 pi times k over n, k 0, 1, 2, etc. are the roots. But these roots themselves start repeating after you reach n minus 1, because by the time you're at little n, you get e to the j 2 pi, which is already covered by k equal to 0, right? So because of this repetition, you just go from 0 to n minus 1. That gives you n distinct roots. And they are, where are they located? If I draw a circle, let me impress you with my perfect circle. What do you think? So there would be, one of them is obviously at 1. Let's make this picture for n equal to, I don't know, 4. Okay? Then you'll have 4 of them located like this. They are, in this case, 90 degrees apart. So basically 2 pi over n degrees apart. Right? If n is equal to 3, then you have 0 degrees, 120, 240, back to 0. So negative 1 becomes a root, obviously, whenever n is even. Right? So similarly, you can look at roots of negative unity. So then you're looking at a polynomial equation like this, x to the n plus 1 equal to 0. That means x to the n is negative 1. So x to the n is negative 1. And I can write negative 1 as e to the j pi. Do you agree that's the same as negative 1? You all see this, right? Yes? Okay. If you don't, I'll give you an amnesty for this time. Look at this picture. Take theta to be 180 degrees. So the complex number is pointing to negative 1. Right? All right. So then to create more solutions, I can just say 2 pi k again, because these are all 1 for integer values of k, right? But when I take the nth root of those, x sub k, the solutions will be e to the j pi over n plus 2 pi over n times k. All right? So those are all the solutions. Again, when you want to plot them, what n should we take? I'm having a bit of a decision fatigue these days, so give me an n. Not too big, not too small. Right? I want my n first, then after. 6, okay. All right, now you're close. Pi by n. So I basically rewrote this thing, right, as, without explicitly writing it, as e to the j pi plus 2 pi k. And then I'm dividing it by n. Okay? All right, back to n equal to 6. So for k equal to 0, we have pi by 6. And that is what? 30 degrees? 30? Okay, so you're going to have one root here. And then they're all 2 pi by 6 apart, which is 60 degrees. So the next one will happen at 90, and so on and so forth. So you get 6. Wait, what am I doing here? I missed something, right? Yeah, this one. Okay, so this is 2. Yeah, okay. These are kind of closer, 30 degrees, 30 degrees. 60 more, and this should be here too. Okay? Anyway, so they're evenly spread. And they all, when you raise them to power 6, they'll all give you negative 1. Well, what? That's not true. Okay. Yeah, this is 30 degrees. Yeah, 30 degrees. So 6 times that will put you at negative 1. Yes. You picked n equal to 6. Don't complain. Zero, because 0 to power n is 0, it won't satisfy the polynomial equation. So we want 1, negative 1 as the nth power. Other questions? Okay, good. So you remember complex numbers, perfect. All right, so now we start getting into complex exponential signals. So since we have e to the j theta, cosine theta plus j sine theta, we can also have signals that look like this, like e to the j omega times t would then be cosine omega t plus j times sine omega t. All right? So either way, you get a sinusoidal expression with frequency determined by omega, right? And sine starts at 0 and oscillates with the same frequency. You know, so e to the j omega t really becomes a nice way of representing a sinusoidal signal with frequency omega without having to worry about whether it's sine or cosine. I mean, sine and cosine only differ by a little bit of phase, right? That's all. And so in this representation, you kind of ignore, where each one starts. So the real part and the imaginary part are individually sinusoidals. And this will help us a lot in the upcoming lectures when we try to break apart periodic signals into sinusoidals. If we were to go into let's break it into sines or let's break it into cosines, it would be a mess. But with this type of representation, complex exponents, it is easy. And we'll see that and we'll appreciate that. All right? So that's e to the j omega t. I mean, you can see the norm, the amplitude of e to the j theta is always 1, right? By definition. Cosine squared plus sine squared, right? So that way you get an amplitude in this function, you get an amplitude that does not change with time. The amplitude is 1. It's just the envelope is 1 and it's just oscillating. Now, if I look at, now we're coming to the main purpose of this lecture. If I look at e to the st, where s is now complex, no longer necessarily real, so let's split it into sigma plus j omega, right? So then this tells us we have e to the sigma t times e to the j omega t. Sigma is real, so e to the sigma t looks like the type of exponential functions we were used to seeing. If sigma is positive, it blows up. If sigma is negative, it converges. But then this type of exponential, real exponential, is multiplied by e to the j omega t, which is an oscillatory thing, right? So what you get then is, let's say sigma is negative, so the envelope e to the sigma t is decaying, right? And then the negative of that envelope will look like this, right? And that envelope function is multiplied by e to the j omega t. So if I look at the real part of this, it's going to be oscillating like this. Right? So this is the real part of e to the st. The imaginary part looks kind of similar. It will be a sine instead of a cosine. All right? If sigma is positive, then it's an exponentially growing function while also oscillating, right? And if sigma is 0, e to the sigma t is just flat equal to 1. So that means the envelope is a constant. And you're simply oscillating. You're back to e to the j omega t. So we get a lot of information from the real part and the imaginary part. All right? So basically we have two pictures here. One for sigma being negative above here. Sigma was negative and there was some omega, right? So this is this picture. And this one is similar. And for this one, sigma is equal to 0 and omega is here. Okay? So if I keep omega the same, the imaginary part is the same, right? This is omega, this is sigma. By changing sigma, I'm just changing the behavior of the envelope. It can grow, it can decay, it can remain constant. What happens if I change omega instead? What if I put my s here? What does e to the st look like? Much more wiggly. So omega is now a bigger number. That means e to the j omega t is a faster changing sinusoidal. So then you'll get a picture like this, except the envelope will be the same because the real parts are the same, but then oscillations will be a lot faster. Okay? So we can do similar things for z to the n, the complex version. So let's do it on the next page. So z to the n, we want to decompose it like we did here, right? E to the st. So in this representation, in dealing with this continuous time exponential e to the st, the Cartesian form was useful because we separated out the real part and the imaginary part, and that separated out the envelope of the signal and the oscillatory part of the signal, right? And gave us a product. When we're dealing with the nth power, the real and imaginary decomposition, the Cartesian one, is not going to work very well, right? So if I did that, I'll get something like sigma plus j omega to the power n. What is that, right? I mean, that's not very useful. Instead, the polar version is easy to deal with. Remember we said multiplication is easy in polar coordinates. Therefore, powers are also easy in polar coordinates. So if we have Rn equal to z equal to r times e to the j theta, which is our polar representation, the nth power is simply r to the n times e to the j theta times n, right? Okay? So what does that mean? It means that if you have let's make a picture here, and I'm going to show you a prettier picture soon. So if my z is, say, j, okay, what is z to the n? The real part is 1, right? What is the angle? Pi by 2, right? So we look at 1 to the n, which is always 1, so the amplitude is constant, the envelope is constant, and e to the j theta n becomes pi over 2 times n, right? If I just look at the real part of this, that means we are looking at cosine pi over 2n. So you start with 1, and then you have at n equal to 1 you have 0, and then you have negative 1, go back to 0, up to 1, 0, negative 1, and so on, right? So that's what the signal, that's the real part of z to the n, when z is, this is an example of course, is equal to j, right? All right, so obviously the amplitude here is constant, it's 1. What would happen if I put it here? Then r is bigger than 1. So that would give me something similar. The oscillatory part is similar. The angle is the same. They are both 90 degrees, right? But I'm going to have exponential growth, right? I will do this, but I'm also growing at the same time, because r to the n for r bigger than 1 is a function that grows. So basically, what determines whether you grow or not is r, the value of r, right? So r bigger than 1 means growth, growing envelope. And r smaller than 1 means decaying envelope. Okay? Now, I'm not going to try to make a lot of pictures here, because at some point in my life, I sat down and prepared this pretty figure to show all of these things, and there you go. So this is back to the e to the st, the continuous case, right? Forget about the discrete case now. We're looking at e to the st. So this is the real axis, the horizontal, the vertical is imaginary. And for several sample points, this picture is showing you what e to the st looks like. Of course, e to the st will have a real part, imaginary part. This is only showing you the real part, so we can have a single plot, right? So if you're on the imaginary axis, that means the real part is equal to 0, so the envelope does not grow. It remains equal to 1. Okay? To the right-hand side, you're growing. The envelope is growing. To the left-hand side, the envelope is decaying. And as you increase the frequency, that is the imaginary part, the oscillations are becoming more frequent. Right? So that's what we already discussed. This is a good picture to look at, like 1 minute a day or something like that, for the duration of this course. And I put it there too, but initially I prepared this for 120. But it was too pretty not to include in 61. Okay, there's a lot of recycling going on. You'll figure so. All right, and this one is more important because it's harder to draw these things on for the case of discrete time. So this shows you several values of z in the complex plane and the resulting function z to the n. Again, that's complex. It's only showing you the real part. So if I look at this ray here, not sure how I highlight that. Maybe this. Same. Okay, so if I look at this ray, can you see what I'm doing? Yes. So here the angle is fixed, right? And the oscillatory part of the signal comes from e to the j theta n, right? So the frequency is fixed by this angle. So as I move these points from here to here, I'm not going to see a change in frequency. What I'm going to see is a difference between decaying envelope, because this has magnitude less than 1, right? And that's what's happening here. Whereas here, you have the same frequency of oscillation because you have the same exact angle, but now you have a growing envelope. If you are on the positive real axis, this is all you can see in a second, right? A real number, real positive number raised to power n. Of course, if it's bigger than 1, you'll get growth. If it's smaller than 1, you'll get decay. So what else? So if you look at, this is what we were discussing basically, j to the power n, that's what I had on the board a second ago. And also important is z equal to -1. Right? So that one, z -1, in polar coordinates means r1, but theta is equal to pi. Right? So you get 1 to the n, which doesn't change, times e to the j pi n. Okay? So that means the sinusoidal part, it has frequency pi. That means you're either e to the j pi, which is -1, or e to the j 2 pi, which is back to 1. So you flip between 1 and -1, right? So that's kind of interesting. So when you put z at -1, z to the n is an extremely wiggly signal. It flips sign at every time instant, right? And if you look at oscillations anywhere else in the complex plane, you don't get a higher frequency of oscillation. Does that make sense? Like here at J, when the angle is pi over 2, there the period of oscillation is 4, right? Whereas at pi, the period of oscillation is 2. It's much more frequent. And if I go to 3J, which is here, again, the period is equal to 4. So these two actually give you the same real part. All right? So as I go, let's forget about the envelope growing or decaying. Let's just move on the unit circle, okay, where the amplitude of the envelope is constant, right? So when I start here, there is no oscillation. It's a flat constant, right? As I go up, I get more and more frequencies. In fact, this happens until I hit -1, that is 180 degrees. And that is the highest frequency of oscillation I can get from a discrete time signal, right? Frequency, the sign flipping from positive to negative, and you can't oscillate faster than that in discrete time. That's the limit, all right? If I go past pi, I'm actually slowing down again, right? In fact, you see, pi over 2 and 3 pi over 2 are the same. There's a bit of reciprocity between the two sides. So that means, this angle here defines the frequency, and theta equals pi is the highest frequency in discrete time. It means that you're flipping sign at every time instant, and you can't oscillate faster than that in discrete time. In continuous time, there is no limit to how fast, right? You can have faster and faster and faster, right? You can't. But in discrete time, things are happening at intervals of a time gap. All right. Any questions on this very important picture that you should look at for a few minutes every day? Okay. All right. Man, I can't believe I spent so much time on this. All right. Back to the notes. Okay, so now we understand complex exponentials after a long detour. Now let's come back to LTI systems. LTI systems are special. They're amazing. They cooperate with us. They're easy to analyze and reason about. So they have remarkable properties, as we've discussed. So here's another remarkable property of LTI systems. All right, are you ready? So one remarkable, very important property of LTI systems is the convolution property. If you know their impulse response, you can predict the output to any other input signal, right? That's number one important thing about LTI systems. A consequence of that is another remarkable property, which we'll talk about here. The response to a complex exponential is the same complex exponential scaled by a factor. Okay? So what that means is, if I apply, say, e to the t to an LTI system, what will come out is some number times e to the t. So the waveform looks similar, it's only scaled a little bit. All right? So when we talk about linear algebra, right, so you took 16AB, you take a matrix A, and you find a vector such that A times B is V times scaled by some number lambda. What do we call these vectors? Eigenvectors. Eigen means self, right? So it's a vector to itself. So we apply that vector to matrix A. What comes out is the same. It may be scalable by that lambda, but the interesting fact is that it's the same vector, only scale, right? So for that reason, we could say that complex exponentials, all of them are eigenfunctions for LTI systems, right? You put it into that system, it comes out intact, except changed in amplitude by a scaling factor. Okay? Why is that true? It's very simple to show that this is true. It's simply a consequence of the convolution property of LTI systems. If I apply e to the st to an LTI system with impulse response h of t, what comes out is the convolution of e to the st and h of t, right? So let's do that convolution. We learned last time that the order doesn't matter. So let's just flip and drag e to the st and leave h alone. So e to the s t minus tau, h of tau, tau became our dummy, so we're integrating from negative infinity to infinity, right? Okay? So now we have e to the s t minus tau, which I can split as e to the st, e to the negative s tau. E to the st has nothing to do with tau, right? I'm doing the integration over tau. T is foreign to that. So I can take that factor e to the st out of the integral. So then I get e to the st, e to the negative s tau, h of tau, d tau. And there you go. This same waveform appeared here. And what is this here? It's the result of some integration, but at the end of the day, it's just a constant, right? If it converges, right? So that becomes our scaling factor. Okay, are you convinced? So what if this was discrete time? Really the same thing. So now I'm going to have z to the n going into an LTI system with impulse response h of n. And what comes out is y of n. And now we do the convolution sum rather than the convolution integral because we're in discrete time. And that is summation over a dummy time variable k. Z to the n minus k, we flip and drag the first one because they commute, h of k. And similarly, z to the n minus k is z to the n times z to the negative k. N is independent from k, and we're doing the summation over k, so z to the n can be factored out. So what remains is sum over k, h of k, z to the negative k. And again, this is our scaling factor. So we applied z to the n. At the output, we got z to the n. Same thing. It was only scaled by that summation term, which is a constant. Okay? So you're convinced this is an eigenfunction. Same thing comes out, scaled by a factor. And you know, for matrices, you have a finite number of eigenvectors, of course. In this case, we have infinitely many eigenvectors because for any S, you know, S lives in this complex plane that's huge, this wilderness, right? You put any point there in the complex plane and look at the resulting e to the st. That's an eigenfunction. Put it somewhere else in that plane, still an eigenfunction. So there are infinitely many of them. Same thing with z to the n. Select z anywhere in the complex plane. Z to the n is an eigenfunction. Okay, so in that sense, this is an infinite dimensional system in a sense because you have infinitely many eigenfunctions. Do you have any questions? So we implicitly assumed here that those integrals and the summations converge. So if they converge, we define them, we attach a name to them. Obviously, you get a different scaling factor when you choose a different s or different z, because this integral here depends on s and the summation here depends on z, right? So the scaling factor is a function of what s or z you have selected. So we're going to give a name to them. We'll call them, we'll reserve a letter of the alphabet, uppercase H. So h of s for a continuous time LTI system will be defined as whenever this integral converges, for those s for which this integral converges, h of s will be defined as h of tau e to the negative s tau d tau. In discrete time, we will again use the letter h. H of z is defined as sum h of k z to the negative k. Depending on your exponent s or the number z, you get a different scaling factor, obviously. And these are the scaling factors. So sometimes these are called transfer function of the system. And the book that I recommended that you buy if you have enough money calls it a system function. I had not heard the expression anywhere else, but whatever you define, that's fine. LTI system. Okay? So naturally, since the impulse response uniquely describes an LTI system, it makes sense that these amplification factors h of s and h of z depend on the impulse response, right? It also makes sense that for different s, I get a different result. So these systems are not going to treat any exponential the same way, right? If I give you e to the t, maybe you'll like it and you'll give it a high amplification factor. If I give you e to the 10t, maybe you won't like it and you'll start diminishing the amplitude, okay? So this whole thing is actually very useful to understand how different s's and different z's are scaled differently. In other words, how h of s and h of z depend on the complex numbers s and z. They are particularly important when we're applying purely oscillatory signals. So if for s, so when is e to the st pure oscillation, no amplitude growth or decay? When s is equal to j omega, right? So e to the j omega t is a special case of exponential functions where you only have oscillations, no amplitude growth. So at this special case, h of s becomes h of j omega, which is h of tau, and remember it was e to the negative s tau. So e to the negative s, but s is now j omega, right? J tau, d tau. So I do this integration, and this now tells me what amplification factor I get in response to a sinusoidal input. I apply a sinusoidal input to my continuous time LTI system with frequency omega. What comes out is another sinusoidal signal with the same frequency, except that the amplitude is modified, is multiplied by this number h of j omega. Okay? And this is critical when we do filtering of signals, because filters are designed to treat different frequencies differently. They sometimes select certain frequencies and let them pass, and they are designed to reject some frequencies. And for certain values of omega, you want this h of j omega to be 0 or at least very close to 0. Okay? And for other values that you want them to go through, you want to make this h of j omega close to 1. Okay? That's basically filter design in continuous time. In discrete time, something similar happens. To take z to the n and make it purely oscillatory, where does z need to live? It has to be on the unit just say circle, dude. You're just throwing circles in the air. Okay, so how do I represent the unit circle? Amplitude is 1, so in our polar representation, r e to the j theta n, r is 1. So we say e to the j theta, right? So then what we get is e to the j theta n as the input signal, right? And then when we substitute z equals e to the j theta in our system function or transfer function, we apply the same definition except that we put z equals e to the j theta. So the definition was h of k times z to the negative k. So z being e to the j theta, this becomes e to the negative j theta k. Okay? And these are really specialized versions of special cases of the transfer functions. In the first case, when s is purely imaginary. In the second case, when z is on the unit circle, right? So they are no different in a sense than our definition of the transfer function, just a special case when s lives on the imaginary axis or z lives on the unit circle. But because of their special meaning that they tell us how sinusoidal things get amplified or attenuated, we call these frequency responses of these systems. The frequency response of the system, which really is a special case of the transfer function. You just put s equals j omega or z equals e to the j omega. So at the end of the day, h of j omega is a function of omega, right? H of e to the j theta is a function of theta. Why don't I just write, some function of omega for the first and some other function of theta for the second, right? Sometimes, it looks weird to have a function with argument j times omega. Even weirder to have something like e to the j theta as the argument. Right? Why not just theta, right? So the reason we'll stick with this is because of the form, this being multiplied by j, and this having the form e to the j something, it will remind us where these frequency responses came from. In the first case, we'll know that this came from a linear time invariant continuous time system, right? In the second case, it will remind us that this was a discrete time system. Okay? This will also tell us this special form immediately indicates that you have some periodicity as a function of theta. So what is e to the j theta plus 2 pi? It is e to the j theta, e to the j 2 pi, but that is equal to 1. So nothing has changed, right? So as a result of this, we have this function h as a function of theta is periodic with a period of 2 pi. What that means is when I'm looking at a picture, a graph of the frequency response of a discrete time signal, nothing matters beyond the interval from 0 to 2 pi. It's just going to be a repetition of the same thing. For that reason, when we make plots of frequency response of discrete time systems, we limit ourselves to the interval 0 to 2 pi. Whereas in continuous time, we go from negative infinity to infinity. Okay? All right, so let's take a short break here, and 5 minutes, and then we'll continue. Hello again. All right, so this is a quick summary of what we discussed. So I apply a sinusoidal input, comes out the same sinusoidal scaled by a factor, right? Same thing for a discrete sinusoidal signal. So we'll see some examples of filtering where the goal is to shape this H so that some frequencies that you prefer go through, H becomes close to 1, others you don't like get eliminated. That means H becomes close to 0 at those frequencies. So let's look at some examples for which we already have some intuition. One of them from the last lectures was the moving average system. I'm going to generalize this a little more because we had only a length 3 moving average system. And why not have a longer or a more general width of the window? So what we're going to do is we'll say y of n is x of n minus k, k going from negative m to positive m. Okay? That is, you start at x of n plus m, go all the way to x of n, and then you go all the way to x of n minus m, right? So to average, what do I need to divide this by? How many terms did I add? 2m plus 1, so I better divide by that, so it's a real average. Okay? 1 over 2m plus 1. Okay. So it is not hard to guess what kind of filter this is, right? If I apply as my input x of n always equal to 1, is that a high frequency, low frequency? In fact, no frequency. I mean, it's just constant, doesn't move, right? 0 frequency, right? So what is the output to that? You're averaging 1. You get 1, right? No big deal. So as you can see, this signal goes through as is without any changes. Okay? So this I can write as e to the j theta n when theta is equal to 0. So the frequency theta in this case is 0. All right? Okay. So now let's look at x of n equal to negative 1 to the n. So it's either plus 1 or negative 1, changing it every time. So is there a signal that moves faster than this? In discrete time, remember, this is the highest possible frequency. And what is the frequency? If I write e to the j theta n, what is theta in this case? Pi. Pi is the highest frequency in discrete time. Okay? Say this to yourself once before you sleep every night. And look at that picture afterwards to see that the one with pi really wiggles really fast. Okay? So what do I get then as the output? You don't get necessarily 0. Now think about it. So you have a sequence of numbers here, right? So you have plus 1 followed by minus 1, plus 1 followed by minus 1, right? But there is an odd number of them. Because of the way we constructed, 2m plus 1 is an odd number. So it's either 1 by 2m plus 1 or negative 1 by 2m plus 1. So a little bit of this wiggly thing passed through after all, right? And let's determine the sign. At time 0, what would it be? At time 0, this is, at time 0, the output at time 0 would be the 1 in the middle, right? and then negative ones on the sides. Well, I guess depends on the width, right? Let's take m equal to 2, right? In that case, you start with, at time 0, the output is 1 over 5, right? So the output is going to be 1 over 5, negative 1 over 5, positive, negative. So it goes through, but then it's divided by 5. If you make the length equal to 3, you'll get 1 over 7, right? Because you're averaging over 7 numbers. And then at time 1, you will be what? Negative 1, right? So I think depending on m, whether you start at the positive or negative value can change, but that's not important. The important part is the amplitude, right? So what comes out is 1 over 2m plus 1 times negative 1 to the n, and somehow m being odd or even is changing the number here, so I don't know how to express this exactly. What should I do? N plus m will fix it, right? Because if m is 2, it doesn't matter. If m is odd, it will flip the sign, right? Okay? So as you can see, you apply negative, it is an eigenfunction, negative 1 power n, went through, only it got scaled by this number, right? But if we take a longer window over which we do the averaging, that number will get smaller and smaller. So clearly you can see the differential treatment here of frequencies, right? I passed 0 frequency, nothing happened. Got a free pass. And then I apply this quickly changing signal, and all of a sudden the rules are different. You squish the amplitude, right? So from that, we can conclude that this is a low pass signal system, low pass filter, meaning that it lets low frequencies go through and it stops high frequencies. Okay? I mean, of course, I only have 2 cases, so we need to do a little more work to convince you that this is generally true, not just for 0 frequency and the highest frequency pi, right? So how do we do that? How can I show you the frequency response in general so we can convince ourselves this is indeed a low-pass filter? Well, we have to do what this says, right? We have to find e to the j theta for different values of theta. Okay. So let's do the calculation. Remember, h of z is defined as a summation over k, h of k times e to the negative k, right? In particular, h of e to the j theta, at which point I'm going to write omega, okay? What I called theta in the previous pages is now becoming omega. Just a quick warning so you're not confused. Because omega in this literature is frequency, okay? So when you see omega, you should associate it with frequency. So then we're going to get k, h of k, e to the negative j, omega k. Now, what is the impulse response? So that means I need to know the impulse response to find the frequency response, right? What is the impulse response of the moving average filter? 1 over 2m plus 1 is the amplitude, right? When you apply a delta, right, in case this is not obvious, when I apply a delta as the input, this filter is not going to know about it until the time becomes negative m, right? Only at that time, delta appears from one edge, right? And then as you slide with this window, delta remains, so I'm getting the same output. And at some point, which is positive m, that delta is going to fall off the window. And then we're averaging zeros again, so we'll be back to 0. Okay? So basically, this is what you get. Something like this. Before that, it's zeros. So this is m, this is negative m. Okay? So this is our impulse response for that filter. Okay? So how do I do this calculation? Fortunately, h, when it's not 0, is 1. So it's not going to be too complicated, right? So if you plug this in here, we're going to get, it's not 1, it's 1 over 2m plus 1, right? So we're going to get 1 over 2m plus 1. And the sum goes from where to where? Minus m to m, because outside of this interval, h is 0, right? So I get e to the negative j omega k. All right, so here comes the more regrettable part of this example. So we have to deal with this term. What on earth is that? Okay. One thing I can do to make this look pretty is to note the symmetry, right? If I have, you know, for m and negative m, I'm going to have something like e to the j omega m plus e to the negative j omega m, right? And I know this is the same as saying 2 cosine omega m, right? So for that reason, I could actually write this, make it look prettier by writing it in this form. Sum k 0 to m cosine omega m. So this is going to be like cosine omega plus cosine 2 omega and all that, right? Still, if m is a large number, you know, if m is bigger than 1, it's not so easy to reconstruct this in my mind anyway. Maybe you guys can do it. So there is a better way of expressing this where you can easily plot out what this looks like as a function of omega. But that requires a little bit of algebra. And that algebra will require remembering some things from before. Have you ever seen something like this? This is a digression now. Forget about anything I said so far. X to power, say, p. Yeah. You've seen series like this? So, oh great, you remember everything. So then you must have seen an identity that looks like this, which makes no sense when x is equal to 1, right? Because the right-hand side is 0 by 0, right? So when x is not 1, this is true. If you don't believe me, do this. Multiply the right-hand side with 1 minus x to the p, and write out what happens. So you get the first term from 1, and then you get to multiply the same thing by x, and that gives you negative x squared, negative x to the p, and negative x p plus 1. So these guys cancel out, you get 1 minus x plus p plus 1. All right? So, all right, why is that useful? What I'm going to do is I'm going to make use of this identity. Yes, did I mess up something? Ah, okay, cool. Yes, K1, thank you. K1, although you don't get points, you already CSI. Yeah, for k equal to 0, it's just 1, right? So, yeah, plus 1 over 2 and plus 1. Thank you, that's really helpful. Okay? I double counted k equal to 0. All right, so thanks. That is the correct expression. All right. WK. All right, thank you. Yeah, okay. Well, let me not go over there again. I mean, convince yourself this is true. Okay? No, the reason is I said you can do that, but it's not very useful. So why should I spend a lot of time to explain what is not going to be very useful? Okay? This basically allows you, by matching e to the negative jm on one side with e to the positive jm on the other side, adding them up, you can represent them as cosines, right? And get rid of these ugly e to the j theta terms, right? That's all I said, but it's not going to be very useful. We'll do it in a different way, right? So the different way I'm going to use is this. And I don't love this because it's a little messy, but it works out in the end. After everything cleans up, it looks pretty. Okay. So what I'm going to do is I'm going to try to write this sum here like that. Okay. So how do I do this? So this looks like this: e to the negative j m plus e to the negative j omega m minus 1, and then e to the j omega m at the very end, right? So if I factor out e to the negative j m, is that how it? No, yeah, it doesn't matter, I guess. I'll mess up either way, so I'll need somebody to watch me. Okay. All right, let's factor out e to the negative j m. In the notes, I did it the other way, so but that's okay. Same deal. All right, then I can write it in this form: e to the j omega, e to the j omega square, and finally I'm going to have e to the j omega to the power 2 m. Is that right? Do you agree with this? And then we have 1 over 2m plus 1, right? Are there any objections to this? If you multiply with e to the negative j omega m, you should be getting this expression here. Agreed? We're all good so far? Yes? Okay. So now that kind of looks like this series, right? 1 plus x, if I think of this as x. Yeah? So how can I represent this now? 1 minus x to the power p plus 1. So that means e to the j omega, and p is 2m, right? 2m plus 1. Divided by 1 minus e to the j omega. All agree? Yes? Now, there's an exception. For x equal to 1, this doesn't make sense. Right? So since x is defined as e to the j omega, what omega should I exclude? 0 or 2 pi. But you already noticed that there's periodicity of 2 pi. If I say 0, 2 pi, and 4 pi already included. Okay, does it look prettier? Not really. We just got rid of the summation. Okay? But we can make this look prettier. Okay? And I'm going to try to do this. I'll do this once. You have to do that kind of messy derivation once in your life. Yeah, so I'm repeating what I just wrote, okay? Well, to repeat, I need to go back in time. E to the negative j omega m. And when things like this arise again in this class, which they will, I'll say, remember in the third lecture on September 5th at 1:31, I had this messy derivation. Something like that makes this work, okay? So we'll rely on precedent. Okay? Okay, 1 e to the j m, what was it, 2m plus 1? 1 minus e to the j omega, is that right, guys? Can somebody check? I'll go back and somebody check if it's the same as the e to the j omega 2m plus 1. Right, okay, so all we did so far was to get rid of the summation. Big deal, so it still looks nasty. Nasty being defined as anything with e to the j, something remaining in this expression doesn't look pretty, right? So how can I make this guy look prettier? Any ideas? Here's a trick. This is a useful trick actually. Anything to do with DSP or in subsequent courses might help you. If I factor out e to the j omega by 2 from this, then it becomes e to the j omega over 2 plus e to the negative j omega over 2. You agree? So why is this better? Because the nasty part, which is this, is separated from something that looks nasty, but we know this is actually a good term. a pleasant looking term, right? So this is really 2 times, wait, that's not true, that's a negative, right? Right. If I were to divide this by 2j, I would get sine, right? The previous sine, omega over 2, so that is the same as 2j sine omega over 2. Similarly, I can look at this expression and I can even out the 2 powers by doing this factorization idea. So I'm going to write this as e to the negative j omega 2m plus 1 by 2 times e to the j omega 2m plus 1 by 2 minus e to the negative j omega 2m plus 1 by 2. Is this even legible? Probably not. But the good news again is that this looks like 2j times sine omega 2m plus 1 by 2. Alright? So at the end of the day, we have this whole expression equal to, let's actually switch to this color. So this is equal to 1 over 2m plus 1 e to the negative j omega m. Coming from this, e to the negative j omega 2m plus 1 by 2 times 2j sine omega 2m plus 1 by 2 divided by e to the negative j omega by 2. Bear with me because there will be a beautiful cancellation now. Everything you hate in this expression will disappear. Omega by 2. Okay? Now let's clean it up. 2j, they go away. Would you believe, okay, so this is m plus 1 half, right? And that will, the m of that will cancel with this, right? And then you're left with e to the negative j omega by 2, and the same thing appears in the denominator. Just like a dream come true. So it's very simple at the end. 1 over 2 m plus 1 sine of something divided by sine of something else. Okay? At least it looks pretty, right? You know, it doesn't look like, you know, e to the j blah blah blah, right? You're asking good questions. Great question, yes. How did it happen? Something went wrong somewhere. This one? This should be negative, right? Where did I go wrong? Something is totally messed up. I knew it was coming. I warned you. Oh, this is e to the negative jm. Did I get that correctly? Yes. What's happening? Somebody help me. GSIs. Rescue. Okay, so this looks correct to me. Okay. 2m plus 1 e to the j omega. Okay. So the top expression is correct. Does everybody agree with this? No, wait. So and then, okay, somebody save me. I'm serious. I'm lost. What is wrong? I mean, do you agree to everything on this page? Yes. You see it better from where you are. If you look at it from here, you see nothing. Power 10 plus 1 divided by that. Okay. So is that expression the same as before? At the top? Looks like it. Yeah, okay, I get it. Sorry. So, okay, so I told you I did it in a different way in the notes, and that's sitting next to me and it's confusing me. So what I factor out should have been
should have been positive this. How am I supposed to see? There are so many expressions. How am I? Okay, is that right now? Is that what you said? Okay, thank you. And the same thing should happen here, right? This should be positive, negative, positive. Okay, so now these are negative 2j's, but big deal, they are both negative 2j. So negative 2j cancels with negative 2j. This is true, this is now positive, right? So the cancellation makes sense now. Okay, so we're good, right? Yes? Okay. All right, good. Okay, so then we cancel. Okay, everything's good now. So what is in the numerator as a function of omega? It's a sine. Now everything we did was true for omega different than 0. So we have to be careful looking at this when omega is 0, right? What would be the answer at omega equal to 0? Omega equal to 0 means you're adding 1s, right? So you get 2m plus 1 divided by 2m plus 1. So the answer is that when omega is different than 0 and 1 when omega is equal to 0. But on the other hand, if I look at this expression, it gives me 0 by 0 when I go to omega equal to 0. But if you apply those rules from calculus, what is it called, L'Hopital or some hospital guy, L'Hopital. So as omega goes to 0, you do the derivatives. Well, the limit of this is actually 1. Okay, so there is no discrepancy with this statement here. So even when in the future, if I write this and don't make an exclusion for omega equal to 0, interpret omega equal to 0 as the limit, which is good. Okay. Anyway, so that means you start at sine starts at 0. By the time I reach 2 pi, how many oscillations have I made? Let's look at an example, make it easier. Choose m to be, say, 3, right? So what are we talking about then? 7 by 2 omega. Okay. Is that right? 3.5. So what does this look like? Then you start with the denominator. Sine omega over 2, right? So it makes only half of a cycle, right? At pi, it reaches its maximum value of 1. Okay? All right, now let's look at n. Right, so there's an oscillation here. I just wanted to see how many cycles there are here. If I choose m to be... So here I have half a cycle fitting, right? Here I should have 2m plus 1 cycles that fit somehow. Okay, so it's going to look like something like this. So depending, of course. And at 2 pi, what happens to it? Pi times an odd number, so sine pi back to 0, right? So it's like this, correct? Okay, so this is the denominator, this is the numerator. So when I divide the two, divide the top by the bottom, it's thinning in the middle, right? There is an oscillatory thing, but in the middle it's thinning, okay? Fortunately, I have notes here for you guys. Needs to load though, like this. Okay, here's what it would look like for, I guess, m equal to 3, I guess, or 2, I don't know, I don't remember. But it's going to look like this. It's sine divided by sine omega by 2, which bevels, and at pi it's the highest, so you get the smallest number, you get a smaller number in the middle. And remember, pi is the largest frequency. Okay? So that means the lower frequencies go through, higher frequencies go through with a smaller amplification factor. So this is indeed a high pass. Sort of. I mean, it's not a monotone response. Low pass, sorry. It's not a monotone response, but not every filter will give you a monotone decay. You know, sometimes you'll have ripples. In this case, this is a very cheap filter, right? You're just averaging. You're not going to get a beautiful frequency response that monotonically decreases. Okay. Let's do one more filter. Good notes. Okay, so this messy business is done. Again, in the future, I'll just refer to this. So another filter, which I'm going to define as follows. 1/2 x of n. This is actually less messy because it's a simpler expression. X of n minus 1. So the rule is this. Look at the input now. Subtract from that the input, the previous input, divide by 2. Okay? What is, so this is a second example. So what is the impulse response of this guy? Is it causal? Okay, so I shouldn't get anything before time equal to 0 in response to an impulse. Right? H of n. So somebody quickly tell me, what value do I get at n equal to 0? And causal, therefore, nothing before n equal to 0. At n equal to 0, I'm looking at the current value, which is a 1, subtracting the previous value, which is a 0, because we have delta at the input, right? So it's 1/2. Okay? At time equal to 1, the value of the input is already back to 0. The impulse has gone. The previous value was 1, so you have 0 minus 1 divided by 2, so negative 1/2. And afterwards, nothing is left. Okay? So what is the frequency response? H of e to the j omega is summation h of k e to the negative j omega k, but k, the only k's that matter are k equals 0 and 1. Okay? So therefore you have 1/2 for k equal to 0 and 1/2 for k equal to 1, e to the negative j omega. How do I make this pretty? Factor stuff out, balance the two sides of e to the j omega. So now I'm going to factor out negative j omega by 2. That way I get e to the j omega by 2 minus e to the negative j omega by 2. Okay? Same trick. Factor out so that you have two exponents with opposite signs, opposite exponents. Okay? That way you can make it into a sine or cosine. And in this case, that's going to be 2j sine omega by 2. Right. Okay. So usually when we look at filters, we worry more about the magnitude of the frequency response, not so much, you know, the phase. So, and this 1/2 cancels with this 1/2. So we're looking at the magnitude of j times e to the negative j omega by 2 sine omega by 2. What do these contribute to the magnitude? J has magnitude 1. Remember when we multiply things in polar coordinates, the magnitudes multiply, right? So this j has magnitude 1. E to the j is anything has magnitude 1. So these do not contribute anything to the magnitude of the product. So they fall out of this absolute value business. So I'm looking at sine omega by 2. And I already know what this looks like. This was the denominator in the previous example, right? Only now it's in the numerator. So 2 pi. And it reaches a peak at pi. Pi is the highest frequency in discrete time. So low frequency to high frequency. The rest, the second half of this plot is sort of a repetition. It's enough to look at the first half, right? So what do you see? If the input has 0 frequency, what goes through?
nothing. The amplification factor is 0. It's completely killed. If the input frequency is pi, you get 1. So the whole thing goes through without change. Okay? And you can immediately see this actually if you look at this equation. If I put x of n equals 1 for all n, clearly y will be, it's all 1s, right? It's always 1 minus 1 by 2, so we always get 0. And that's basically this behavior. At 0 frequency, constant amplitude signals, nothing goes through. Low frequencies are gone. And then, if x of n is negative 1 to the n, and that means I'm here, what is y in that case? Negative 1 to the n, and then the previous value will have the opposite sign, so it will have 2 times that, right? And you'll get exactly the same signal. And that's what you're observing. The amplification factor is 1. Okay? So this is a high pass filter. Alright? Alright. So, okay. Any questions? Yes. We'll see later that 0 to pi tells you everything you need to know. If your LTI system has an impulse response, that's all real. Okay? In that case, there's some kind of symmetry between 0 to pi and pi to 2 pi, which is exactly what you're seeing here. So the first thing we observed is that the whole thing is periodic with period 2 pi, so we need not look beyond 2 pi. With your observation, with this symmetry, actually you can only look at 0 to pi. Yes. Okay. So the reason is, so here we have, so this is what I'm looking at the magnitude of, right? I mean, this bottom replaces this top, right? So it's a product of things, right? So when you have products, the magnitudes multiply and the phases add up, right? But I'm only looking at the magnitude, right? So I can look at the magnitude separately. So the magnitude of the whole thing is the same as the magnitude of j times the magnitude of e to the negative j omega by 2 times sine omega by 2. Do you agree with this? And j is a number that lies here. It has magnitude 1. E to the negative j omega by 2, whatever omega is something that lives on the unit circle, so it has magnitude 1. Yes. Building this rule, it will be software, not circuit. Discrete time stuff you just write code, right? I mean, you just say, look at the current value, subtract the negative value, spit out the difference. Okay? I mean, if you want a digital circuit, then you can use memory registers and delay the input by 1 and subtract from the current one. So it would look like something like this. So X comes in, goes through, and then gets delayed, and then you subtract and divide by 2, and here comes 1. Okay? Alright, so here we talked about 2 examples. The first one was a moving average system, y of n, which in our previous example last time was, I'll just write this to keep it shorter, x of n plus x of n plus 1. And the example we just saw was just a generalization of that. And then the other example we saw was 1/2 x of n minus x of n minus 1.
Okay? The impulse response for this guy is 1/3, 1/3, 1/3, and all zeros. And the impulse response for this guy is 1/2, -1/2, and all zeros. Right? So if I look at the impulse response, it only has a finite lifetime, right, in each case. So systems whose impulse responses, too many S's in this, are finite length, finite duration, are called finite impulse response systems. FIR for short. Okay? So the most general form of a causal FIR, this guy is not causal, right? I could make it causal by doing x of n plus x of n minus 1 plus x of n minus 2. Essentially the filter characteristics don't change, you just get a little bit of phase. Causal FIR system has the following form. Y of n starts with some number, let's call it b0, times x of n plus another number xn minus 1. And depending on the length of duration, which is finite by the FIR assumption, you have a length m, and the last coefficient will be b sub m x n minus m. Okay, this is the most general form of an FIR filter. And what is the impulse response of this? It's very easy. You can read it off from the coefficients in this equation. Before the impulse comes, you know nothing, it's a causal system, right? At time equal to 0, when x is set to be an impulse, right? Delta of n gives you what? Time equal to 0, only x of n is equal to 1, everything else is 0, right? So before that everything was 0, now you got b0. At time 1, I'm going to separate out the times so they match up here. Okay. What happens at time 1? Everything is 0, x being delta, at time equal to 1, only this term is equal to 1, everything else is 0, so I get b1. And then at time 2, I get b2. And at time m, I get bm. And afterwards, there is nothing left. Okay? So the coefficients in this difference equation become the entries of the impulse response. So it's really easy to see the impulse response of a finite impulse response system. And obviously not every system is FIR. If it's infinite, we call them infinite impulse response. Response. And guess what? We call it IIR. Alright? We've seen examples of this. One was the so-called accumulator, right? Accumulator adds up the values of an input, x of n. So we assume that at the time that the input arrives, let's say the time is 0 at that time, everything up to that point was equal to 0. So the system was initially at rest, so we take this initial condition to be 0, right? So we discussed this before, and we know the impulse response. What is the impulse response? You've seen it twice. In lecture 1, lecture 2, you're going to know this. You're getting zeros, right? You're adding zeros, so you're at 0. You started at 0, right? And then an impulse comes. You switch to 1, and the impulse disappears, so you stay there. You have nothing else to add to it, right? So you get unit step. Okay, unit step looks like this. But it never goes away, right? So it has infinite duration. And that's why this is an example of an infinite impulse response
systems. So difference equations in discrete time or differential equations in continuous time are a great source of LTI systems if they are constant coefficient and linear difference or differential equations. So I'll just write this for a discrete time system. So linear constant coefficient difference equation. We'll write a general form as follows. So we're going to write some number a0 y of n plus a1 y of n minus 1 plus a n y of n minus n equals some number b0 x of n to dm x of n minus n. Okay? This is the most general form of a difference equation. The numbers n and m can be whatever. They can be different from each other too. So the FIR systems we looked at on the previous page was really a special case of that general representation, right? We don't have any yn minus 1, yn minus... We don't have any past values of y. We're only looking at x and the past values of x. So we only have the right-hand side of that. Okay? So all of these, so a1 to an are 0 for FIR. Okay? So we also make the assumption that this leading coefficient a0 is different than 0, because if it's 0, then you lose causality, right? The highest term will now be something like y of n minus 1, and that will depend on x of n, which is in the future. So to fix causality, we assume a0 is different than 0, and then on the right-hand side, we don't allow anything that depends on n plus 1 or higher. Okay? And usually, because we can divide everything by a0, typically we assume a0 equals 1. All right? So the presence of these terms essentially make the system infinite impulse response. Okay? All right, I will stop here, but it's important to think about why this system is an LTI system. So think of all the scaling homogeneity properties. Okay? So from that you can see the linearity, and time invariance is a result of the fact that the coefficients a0, a1, b0, b1, etc., they don't depend on time. There is only one rule here for generating the output, right? With fixed coefficients. And those coefficients do not change over time. That makes the system time invariant. Okay, see you next time.